at this point P right here using Gauss's law of electricity. So first thing I need to do is to create a Gaussian surface. In other words, this is not a physical surface we're putting here, it's sort of imaginary. It's a virtual surface. So I'm going to do a cylindrical So basically, I've got this, imagine a string and I got a can sitting, that's the string is going right through the middle of the can. Right on the edge here is my point P. So we'll make that a distance R away. I know that the total electric flux is equal to the enclosed charge divided by epsilon sub 0. Oh, by the way, some spelling things I saw when I was looking at the flash quizzes. I didn't take off for it, but just separate has a rat in it. It's not separate, it's separate. It's an A and not, epsilon sub naught. But just side notes. All right. So, recognize we basically have three surfaces here. We have the two end caps, and then we have the side of this can, of this Gaussian can. So my flux would be the flux through the left side, plus the electric flux through the right side, the end caps, left cap, right cap, plus the electric flux through the sides of the can, through the, I guess, cylindrical side, however you want to denote it, this part. And that's equal to the total enclosed charge over epsilon sub naught. The reason we can exploit the symmetry here is we know the direction of the electric field coming off of this line. We went through that rationale before, that for at point P, we have just as many charges to the right of that as to the left of it. In other words, my electric field, any sideways component is going to cancel out. I know the electric field is that way. Anywhere off that line, it is away from the line. So my electric field here is pointing in that direction. Over here it's pointing in that direction. Here it's pointing in that direction. Here it's pointing in that direction. There it's pointing in that direction. What is the direction of the area vector on the left side? Got one person pointing in the right direction. Two, 3, 4. All right, we've got sort of a rolling along here. Don't forget, the area vector is perpendicular to the surface, and since this is a closed surface, it's pointing away. So the area vector is that way. So what is the dot product between the electric field and the area vector? 0. Yep. 0. Even though the electric field's not constant, but it is, the direction is constant. Right side, same argument. My area vector is pointing to the right. My area vector on the sides are pointing in the same direction as the electric field. The area vector is pointing always perpendicular, which would always be away from that central line. So what we are left with This is the electric field at the surface, so at point P, because it's basically the same magnitude at point P as it is anywhere on that surface, times the area of the can, of the side of the can, which is 2 pi r times, I do need to give a length here. Call that L. 2 pi r L. That is the electric flux. The charge enclosed, well, I have a uniform linear charge density. Did I used lambda before, didn't I? Yeah. So lambda is equal to the charge divided by the length. It's uniform, so I could make it differential if I wanted, dq over dl. I don't need to. So my charge is just lambda times the length that I'm looking at, so that would be lambda times my length L there, so this would be lambda times L divided by epsilon sub naught. So my enclosed charge divided by my constant. And so my electric field at point P, the magnitude of my electric field at point P, L conveniently cancels out, and I'm left with lambda over 2 pi epsilon sub naught r, which should be what we derived when we did it before. Which would also be 2k lambda over r. Questions here? All right, infinite sheet of charge. Infinite sheet of uniform surface charge density. Again, I can exploit the symmetries here. I know that the electric field is going to be going straight away out of the sheet there, because all the components that are parallel to the sheet will cancel out. From a side view, I got my infinite sheet here. My electric field is going out away. This is an infinitesimally thin sheet, and the reason I say that will become of importance later. So let's set up our Gaussian surface. I'm basically putting a can like that. And that is absolutely horrible. For people struggling with the visual on this one. Imagine that's my infinite sheet. And so that's my Gaussian surface right there. Where the electric field, so if I want to find the electric field at point P, I'm just making the can long enough so that this surface is at point P, or that one of those surfaces is at point P. Go ahead and make it official, point P. So we start out with the same thing right here, boom. Start up high. So my electric flux through my surface over there is equal to the enclosed charge over epsilon sub naught. I have three parts to my surface there. I've got, I guess from your point of view, the right end cap, the left end cap, and then the surface. There's no reason to treat these as different surfaces, but you can if you wish. So left cap plus the electric field, right cap, or electric flux, sorry, right cap, plus the electric flux side is equal to the enclosed charge over epsilon sub 0. So based upon the direction of the area vector for each of these three parts and the direction of the electric field, which one of these is equal to 0?
This side.
Yep. But at the end caps here, my electric field and my area vector are in the exact same direction. So I'm going to make up a radius here of, let's see, I'm just going to call that R. That's the radius of my can. Well, my electric field everywhere along that surface, it's constant, and so it becomes E times the area of that surface, which is pi r squared. On the right side, it's E times pi r squared. And then my charge is just the surface charge density times the area. So it's sigma times pi r squared over epsilon sub naught. And conveniently, pi r squareds all go away. So I'm left with 2 times the magnitude of my electric field is equal to sigma over epsilon sub naught, or my magnitude of my electric field is equal to sigma over 2 epsilon sub naught, which is exactly what we derived when we did it before. Questions to hear? You know, let's take a small little 5-minute break here, and then we'll come back and exploit this stuff some more. Let's see, setting up.
Are you ready for your speech tomorrow?
No, I'm super nervous. I've rehearsed it a couple times, but I'm like shy. I don't want to go up there. You did really well in your speech.
No, I was very nervous.
I'm sorry?
I was very nervous.
Did you practice a lot?
No.
Yeah. You did very well. I think you did probably the best out of everybody that went the first day.
Really?
Yeah. I think everybody did pretty good overall.
At some point, I just got tired of writing electrostatic equilibrium, so I've now abbreviated it. In other words, the charges, if I put excess charges in there, they basically settle down where they're going to go. I'm not going to say there's absolutely no acceleration, because these particles are vibrating around and moving around the nucleus, but we can treat it like the particles that settle. All right, we've talked about before about what happens to the charges. Try that again. Where do excess charges show up in if I have a solid conductor? Once the charges are in electrostatic equilibrium.
Outside?
Yeah. We'll make them negative charges just because it's easier to draw. And we've derived it already in terms of force of a charge in the middle, but let's use Gauss's law. I'm now going to create a Gaussian sphere in the middle right here. I know that the electric flux is equal to the enclosed charge over epsilon sub 0. In other words, E dot dA is equal to the enclosed charge over epsilon sub naught. So what is the enclosed charge in my Gaussian surface? And again, the Gaussian surface is in black here. The purple is the actual physical conductor.
Yeah.
But since all the excess charge is on the outside, indeed, this is equal to 0. Now I definitely have a surface area here. The only way that my electric flux can be 0, since I have a surface, is if the electric field is 0 inside. And that is one of the shortcuts that we've talked about before, but it's one of those shortcuts that we definitely will be using, especially in this next problem. All right, so questions about yet one more way of looking at the electric field being 0 inside a conductor in ESE. All right, so the shaded, the hash marked areas, that is actual material. Those are conducting, these are part of conducting materials here. What is the electric field here? Where the green dot is. Assume it's in electrostatic equilibrium. Apparently what I wrote over here did not make a huge impact on people. Inside a conductor that's in electrostatic equilibrium, what's the electric field?
0.
All right, so when I'm right here, what's the electric field right here?
0.
Yeah, 0. What about right here?
0.
Okay. So if I create my Gaussian surface, again, this is just a virtual surface for using Gauss's law. I create my my Gaussian surface right there, so that my radius puts me right in the middle of that conducting sphere. I guess I called it a ring, it's three-dimensional. My electric field everywhere on the surface of my green sphere is 0. So what is the total electric flux through this surface? Yes. So therefore, what is the total enclosed charge? Has to be. Therefore, since excess charges hang out on the surfaces, and I got two surfaces, I got an inner surface and outer surface, what is the electric charge that is on this inner surface here?
Can you please repeat your question?
All right. So we established that the electric field inside my conductor is 0. We established, therefore, the flux is 0, and therefore the total enclosed charge is 0. Therefore, since excess charge has to be on the surface, and I have two surfaces here, what is the total electric charge on this inner surface here?
Would be the 5 nanocoulomb?
Unless I missed a word, no. The total charge has to be 0, because again, my electric field is 0, so therefore my charge has to be 0.
0.
Nope. I forgot, I get negative 5 nano, oh, sorry, I have a 5 nanocoulomb point charge right there in the middle.
So negative 5
Yeah.
nanocoulombs?
Gotta be negative 5 nanocoulombs. I got negative 5 nanocoulombs sitting right there, and that is all blurring together, so let's go for. I need my total charge to be 0. So on this inner surface, I got negative 5 nanocoulombs spread throughout that whole thing. I have a total of negative 10 nanocoulombs on this ring. So what is the charge on this outer ring here?
10.
Yeah.
It's not 10.
Which surface?
Won't be positive 5.
Which surface?
The outer surface of the sphere. I am going to make one small change here, so sorry. Let's make this a positive 10 and a negative 7. Just because I think we had more interesting numbers. All right, so we know this is negative 5 on this inner surface of this hollow sphere, so that the total charge is 0. But I said that there's now positive 10 nanocoulombs that have been dumped on this ring here. So the net charge of this ring better be positive 10 nanocoulombs. So what is on this surface here?
15.
So we just said it?
15.
Yep. Because my total is 10. What is the total charge on this inner surface of the larger sphere?
Negative 15.
Yep. And what is the charge on the outer surface? Yep.
Can you go over how you got 15 again?
All right. Let's see if I can sort of do a cross section here. So I have 5 nanocoulombs sitting in the middle. Then I've got a conductor there, got a conductor there. I know that my electric field here is 0 inside my conductor. Since my electric field is 0, my total flux is 0, which means the enclosed charge has to be 0. So therefore, I have to have negative 5 nanocoulombs sitting on the inner surface here so that the total charge is 0. I also said, once I made the change, that the total charge of this hollow sphere here is 10 nanocoulombs. So whatever goes here, I know the total has to be positive 10. And so therefore that is 15, positive 15 nanocoulombs, so that the total is 10. Same argument, the electric field equals 0 here. So this has to be negative 15 nanocoulombs, so that the total enclosed charge is still 0. The total charge here has to be negative 7 nanocoulombs. So I have to have positive 8 nanocoulombs there. Let's come up with some distances here. Actually, I'll do it over here. So this would be R is equal to 0 right there. And then let's make that 1 meter, 1.2 meters, 3 meters, 3.4 meters at each of the surfaces. And what I want to do is if I come out to here, where R is equal to 6 meters, what is the electric field at 6 meters away? Oh, let's just make the magnitude of the electric field 6 meters away. How would you solve it? There's several ways. There's a short way of doing it, and then there's several longer ways of doing it. Probably one excruciatingly long way of doing it.
Can you treat it as a point charge?
Why can you treat it like a point charge? The answer is yes, but why?
Is it because it's uniform?
Yes, and one more, and the fact that it's spherical symmetry.
Oh.
I can still have a uniform charge on a line, but I can't treat it like a point charge if it's a liner charge. Yeah, because I have spherical symmetry, if I'm outside of that, I can treat it like it's a point charge. And so this would just be K, Q, well, the total charge over there, which is 8 nanocoulombs. I guess that's 9. E9. Divided by the distance squared. So that's 72 over 6, which is 12. Just KQ over R squared. Treat it like a point charge. All right, questions to hear?
Isn't it 72 over 36?
Oh, over 36. 2. All right, let me do a quick check, see if there's anything else from 26 I wanted to talk about. Oh, no, sorry, 25, not 26. Plenty of stuff in 26 I want to talk about. I got it there. All right. So, exciting news. We're done with 25. We're about to start chapter 26. So how about the quiz on 25? 2 weeks from today. The math said it's 25. Sort of sensing a pattern here. What also makes this more exciting is that once we're done with 26, then we'll start talking about when the test is. Woo!
Can you take a picture of that and maybe send it in the chat? Thank you.
And I will also say that test 1A, in my opinion, typically is the hardest of the tests. Just the nature of the material.